in Mumbai, at least it is. I mean, of course, in Maharashtra, it is a very high.
Access situation is not good. Earlier, for example, BRC employees hardly got infected, but now there are many. But then I have hardly heard any death, so more or less people are getting cured. So
yeah, no. I mean, I think there is this is kind of muted.
Yes, but this is something it upsets everything in the sense whole system. If one is getting infected, then everybody in the office, whoever interacted, they cannot come to office for 14 days. The family, this, that. So and driver. Suppose one driver is infected, then driver, then contact tracing is there. Then whoever use that vehicle, all are getting contact. So this kind of problem is very much there. Otherwise, okay, life is not that bad. Hello. 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 I'm not able to hear. There is some problem.
So we can hear you. So we can hear you.
Okay, sorry. I thought you were. So we'll be starting the presentation in another 1 minute, right?
Yes, Vikas sir will join. He has been disconnected.
Okay, good. Yes, now it is 12:06. I think we should start, right? Hello? Hello?
Sir, I'm calling Vikas sir.
Okay. Yes, Professor, because the tool is back. So, should we start the session? Hello? Can I start the session?
Sir, please unmute. Sir, sir, please unmute yourself. Vikas sir. Sir, please unmute yourself. Unmute yourself.
Because the microphone to off আছে ওটাকে অন করুন হ্যাঁ
Hello.
yes
Is okay?
yeah, it is
Okay. Huh.
Yes, so I will be starting or some organizers will be giving me go ahead. Hello?
Hello. Yeah.
Yeah, can I start the session?
Yeah. I can start now.
Okay, now before that I'm asking the organizers. So can I start the session?
Oh, I see.
Is there? Okay, let me start because the time is running out. So good afternoon. This is the third annual conference on quantum condensed matter, QMAT 2020. And this is the fifth day, and we have the second session, second parallel session. And I am Professor S.M. Yusuf from Bhava Atomic Research Center, Mumbai. And it is my privilege to chair this session. And I thank all the organizers for this opportunity and organizing this nice conference. It is a series. It is a really nice initiative from all the organizers. And in this session, there are 4 talks, 2 talks each of 30 minutes, followed by 15 minutes to short talks. And the first talk will be presented by
shall we start now?
First talk will be presented by Professor Vikas Chakravarti from S.N. Bose National Center, Kolkata. So with this, and I'm really privileged because he's my teacher. I have been interacting with him right from the day I did my post-chemistry at SIMT. So with this, may I invite Professor Vikas Chakravarti to deliver his talk. The total time, including discussion, is half an hour. Okay, so please.
Okay. So, hello. Can you hear me now?
Yes, yes.
Okay. So, thank you. And thank you, the organizers, for giving me this opportunity to share some of the work that we have been doing for maybe 3 decades, over the 3 decades, with various people, Orunabo Chakraborty, Arnab Das, Sudip Mukherjee, Atanu Rajok, Purushottam Ray, and so on. And it will talk about, essentially quantum annealing, but it will be a prelude to that. And I will come to some of the technical things just after 2 slides. And let me do that. In these slides, I will try to give a qualitative picture, and then we will go through the technical things a little faster, but I will try to motivate you from those two slides. Now, can I go to the next slide, please? Now, you can see that, I mean, on the left-hand side, you have kind of free energy landscape, energy or free energy landscape. Suppose we take this is typically for a many body system. Now, I generally, as an example, I will consider, say, for example, n Ising spins, and they are interacting. Typical maybe ferromagnet, but that's not an important thing. Antiferromagnet will also be doing that. Some disordered magnets will also do that. This top left one is a kind of double well potential. I mean, either the energy or free energy on the y-axis, and you have the spin configurations. Now, for each spin, Ising spin, you will have, for each spin, there are two states. So if you have n Ising spins, and you can see the free energy or energy like this, that, I mean, it's a double well kind of thing. Typically, the barriers, I mean, are of the order of n. I mean, the walls are also of the order of n. I mean, if you have each spin having and the neighbors in the opposite way, then the domain walls are the highest. Then, of course, you will get the walls. But typically, if you have domain walls sharing many spins, then you have the domain wall of the order of n, but it's not exactly n, but it's of the order of n. Both sides of the domain wall are symmetric. So although it's an since there is an order of n barrier, the system cannot go in the thermodynamic limit from one well to the other. That's why, I mean, a ferromagnet in my home is still maintaining the north-south polarity for many years, and but it will be different in a nanomagnet where n is small because the barrier is small. So, but in the thermodynamic limit, this is also, but this can be considered an ergodic system because both sides are related by symmetries, and I can do the statistical physics for one part of the well and so on. If you take the order parameter, I mean, kind of Landau suggestion that, I mean, you can kind of characterize this kind of system with an order parameter, which may be magnetization in this case. For a finite system at a finite temperature, there will be a fluctuation of this order parameter, and you can see that order PO on the right-hand side of Landau case shows like a picked one, and it will gradually, I mean, as n increases, this will become narrow, and the peak will be at exactly at the order parameter, and that will go to 0 when you have one well, and otherwise it will be at a finite point. So this is the typical thermodynamic scenario for a many-body system where you have unique ground states, and then you have the order parameter distribution looking like a delta function in the thermodynamic limit. Come to a kind of very special kind of disordered magnet systems, but this is very generic. Whether it is neural network, traveling substance problem, we have a similar kind of scenario. It's called spin glass, where the disorder cannot, I mean, the Landau scenario, as we said, I mean, it is not necessarily for a pure ferromagnet. It can have disorder and all these things, but these phased away, so you can get essentially this picture. But the thermodynamics will completely change, and the free energy landscape will look completely different if you have something like this, that on the left-hand side, but below the upper one, you can see that the free energy landscape or energy landscape of a Sherrington-Kirkpatrick spin glass model typically looks like this. It has also a symmetric part as in the upper ferromagnet. I mean, it has a symmetric part. Somehow I didn't draw it. Out of the 2 to the n configurations, there are few where, okay, so you have a kind of very rugged landscape. You can see that there are some local minima, then some global minima, and so on. But unlike in the kind of Landau scenario or in the ferromagnet case we sketched above, it has a different thing, which is something like this, that these local minima, local hills are actually coming from that. I mean, you can make some flips of the of your spins in the neighborhood, and then you can get either, I mean, you can get, I mean, few spins flipped, a finite number of spins flipped, you can go to another minimum. Then yes, a few more will make it higher, but I mean, then if you do it a little more, but still in a local way, you will get another minimum, and that way you can see that you can come to a minimum, but occasionally you have to go above the hill. That may be small, and eventually when it is of the order of n, that means you cannot do a get by perturbing, say for example, starting from the right hand side, you cannot come to the real minima shown here. I mean, this is just an indication. You cannot come to that by perturbing, and you cannot even come by doing a typical search that we do usually in our ferromagnet case, that if you change the configuration and if it gives a lower energy or free energy, you accept it. Then you come to, I mean, anything higher, you just throw away. So you will come to the global minimum on the top scenario. But in the on the left side bottom scenario, you can easily see that this strategy will never work. You cannot just throw away some changes. And of course, if you knew that where is the minima, then of course there is no problem. You can do that kind of things. But if you do not know, as is the case of
Professor Yusuf, none of us can hear anything. So would you intervene?
Yeah, in fact, I'm also not getting his voice.
Hmm.
This is the problem. And it is stuck to the second view graph. Hello? Hello?
Hello. Hello.
Yeah, Professor Vikas Chakraborty, I think he has left the meeting, it seems.
Okay.
The
So
speaker has left the
can
meeting.
I call him? I mean, I have his number. Can I call him?
Yeah, please.
Okay.
Hello, would you contact Professor Vikas Chakraborty? Hello, I am talking to organizers.
Yeah. Hello, sir. So just I called, sir. Hello. So
Yeah.
can I talk to this system host actually, because sir is telling that he's trying to connect, but like
Huh.
is yeah, ma'am.
Yes.
Yeah. So actually I called to because sir he's telling that like he's trying to connect, but
Hmm.
like it's not allowing him. So are you
There
getting any?
we have allowed everybody. There's no should not be any issue. I think he has some
Okay.
problem with his internet connection.
Yeah, maybe that is the reason.
My voice
So
is now clear, right? Because
Yes. Your voice is clear.
yeah.
So,
In fact,
tell us this something.
before starting this session, I was waiting for some go-ahead signal from you, but somehow then I started on my own. So I don't know whether it was a communication problem or not. I don't know. I didn't get hear from you.
So,
okay.
shall I suggest something?
Yeah, please.
He can try to. I mean, he can call to like someone, the system admin, through the
Okay.
phone, and the system admin can put on the like this speaker mode. So, and the slide anyway see is changing. So that way, I think it can work, and he can see his slides and always whenever change.
But then his voice has to come, right?
Yeah, but it's through the phone. Right now, he has a
Okay.
problem with the
That's it.
internet, I guess.
Sir, he cannot see the slides, na. He cannot, if he cannot join, then he cannot see the slides,
So
how it is
he can
changing.
read on the computer. He can see the same slide on the computer.
Um,
Yeah,
com-
number wise
okay.
we can go. Next. Yeah.
I think
Try
that way
this.
he can try to join.
So I'm sending.
Okay, let me call him.
Is he back? Hello, voice is very low. So because Chakravarti, are you getting me?
Is not picking up the phone.
So in the current scenario, the student shift, it is already 12:26.
Sorry.
Should I move to next speaker or we'll wait for another until his time, you know?
Yeah. So yeah, I mean, we'll wait for 1 minute, or probably we'll move to the next speaker. And
Because
then
his scheduled time is 12:05 to 12:35. So 12:35, until that we can wait.
yeah, that's true. So I mean, what we can do is, like, we can take the next speaker. When he joins, then we can tell him that he can continue at the end.
হ্যালো স্যার, হ্যাঁ স্যার কথা বলুন স্যার।
Yeah,
ক্যান ইউ হিয়ার বিকাশ স্যার?
Hello.
Yes, we are able to hear you. So
স্যার আপনি এভাবে কি করতে পারবেন? হ্যালো
Hello.
হ্যাঁ স্যার, আপনি কি এভাবে আপনার ফোনে
98304096 একটু ফোন করতে পারবেন? তাহলে আমি এইটাকে ইউজ রাখতে পারি।
30
9830408686
9830
হ্যালো।
হ্যাঁ
আপনি আমাকে একটু 9
Tell him to send the message or forward that number.
you can type a message to the number, that mobile number. Actually, you are coordinating from Asian boss, so he could have come over there.
So shall we do that? We can take the next speaker, and then at the end we can do.
Almost, because it is 28. No, I mean, as per the schedule, if someone else plans to join that particular talk, then we should maintain the time. Otherwise, that will be another problem.
Yeah. But if we keep delaying, delaying, then it will be even.
No. What I mean to say that we'll start at sharp.
আমাকে ঢোকাবেন? তাহলে যাচ্ছে না মনে হচ্ছে।
না আপনার, হ্যাঁ আমার স্যার, আমার তো এখানে পুরো কাটাই আছে, আপনি নেই এখানে।
তাহলে আমি আবার ঢুকছি।
হ্যাঁ অ্যালাউ করার স্যার কিছু নেই, আপনি ঢুকে যেতে পারবেন। তাহলে স্যার আপনি এভাবে কি কথা বলে করতে পারবেন? আমি আপনাকে ফোনে ধরিয়ে দিয়েছি। হ্যাঁ আমি সেটাই মনোরঞ্জন স্যারকে বললাম, যে আপনি তো দেখতে পাচ্ছেন, আপনি কি আপনার ল্যাপটপে দেখতে পারবেন? হ্যাঁ আপনি আরেকবার, আমি আরেকবার একটু ট্রাই করুন রিকানেক্ট করা, ঠিক আছে? হ্যাঁ আচ্ছা আমি এটা হোল্ডে আছি, ঠিক আছে।
I can see the next speaker.
হ্যাঁ প্রিপেয়ারিং ফর মিটিং, আপনি ওখানে ঢুকে যাবেন স্ট্রেট, আপনাকে কিছু আর করতে হবে না। তাহলে স্যার আপনি ফোনটাকে রিস্টার্ট করুন, একবার অফ করে একবার রিস্টার্ট করুন পুরো ফোনটা, মানে পুরো সুইচ অফ করে দিন। হ্যালো হ্যাঁ
So what do you do? It is just 5 minutes left as per the schedule. Now it is 4 minutes.
You are the chairperson. You can take.
Yeah, I understand, but still I need some feedback from the organizers.
Yeah, I mean, what we can think of, take the next speaker. I mean, if he is not able to join, And then
Okay.
at the end, we'll see that like if he is able to join, then we'll continue.
Okay, fine. So we'll take a call in another 2 minutes.
Yeah, yeah. At the end, we'll see that if he
Yeah,
is,
he can be accommodated. Yeah,
yeah, yeah,
because we have the lunch break, so probably it is possible. You know.
yeah. I mean, yeah. This is unfortunate. He tried a lot. I mean, unfortunately, his laptop is not working. I'm sorry.
Is it over last 4 days this kind of problem happened quite
No, 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 no.
often or no?
First time. This is first time because of the mobile. He's trying to do it from
Oh,
mobile,
I see.
and his laptop has a old Ubuntu version, so that's why it was not working there.
Mhm.
And actually, he checked and everything was fine. But then now
Yeah,
it's,
yeah. Before the session starts, he was absolutely fine.
yeah, he tried his best to like get things straightened out.
Okay, so I think I'm taking a call. I think let us move to the second speaker because we have only 2 minutes left. So end of the session, if Professor Vikas Chakraborty can, we can get him back. We will manage during the last break. Okay. So yes, let me request Professor Jogesh Singh from ISR Mohali to deliver his talk, and he will be on field-induced quantum critical point in the.
Hello.
Can you hear me? Am I audible?
Yes, yes.
Yeah, very
Okay, so I will share my screen.
So your total time 30 minutes, including discussion. Okay. So after
Okay.
25 minutes, I will sound it.
So my slides are visible?
Yeah, very much.
Okay. Thank you, Chairman, for the introduction. I also thank the organizers for the opportunity to speak here and congratulate them on putting together a wonderful program in spite of the difficulties. So I'm going to talk about field-induced quantum criticality in the heavy fermion material ytterbium-2 iron-3 silicon-5. And I gratefully acknowledge funding from DST, SERB, and the University of Tokyo.
You have to raise your voice level little low.
Okay.
You have to put the microphone properly.
Right. Okay. What about now? Is it better?
Yeah, now it is better. But when you speak, it moves away from your,
Okay, I will try. So most of this work was done while I was on sabbatical at ISSP, University of Tokyo. So I had the privilege of working in the groups of these gentlemen. So these are my collaborators and I acknowledge them. So the plan of my talk is the following. I will try to introduce classical and quantum phase transitions and telling differences between each other. Because this is my first foray into this field, I'm also learning. So I chose to give this talk so that I could force myself to collect the data and have a look at what the results are telling me, etc. So I look forward to comments and suggestions from the experts in the field. Then I will tell you why we chose this particular material, and then move on to the results, which show that at field h equals to 0, we have a heavy fermion condolattice material, which undergoes an antiferromagnetic transition. And this transition can be tuned continuously to 0 temperature, reaching a quantum critical point. And I will show that the behavior of the system at the quantum critical point is non-Fermi liquid-like. I'll then conclude. So a classical phase transition is any transition which happens at finite temperature. as shown on the x-axis here. If I cool from high temperature down to low temperature and cross this shaded region, I will enter an ordered phase. And if by some control parameter like pressure, field or something, I can tune this ordering continuously down to t equals to 0, then I will reach what is called a quantum phase transition or a quantum critical point. To understand the differences between these two, let me start with an experimental example. The simplest experimental example is the Ising ferromagnet in a transverse magnetic field. So the data is shown here for lithium holmium F4. So holmium has a huge moment, 7 halves, and therefore this is like an Ising spin, which means that the spins can only point either up or down. So because of interactions between these moments, the magnet orders ferromagnetically at 1.5 Kelvin. So in the thermal paramagnet here, we can look at this diagram here to understand what is happening. So both the up and down states are like a double well, and the kinetic energy, the thermal energy is large enough so that the up and down spins can tunnel from one to the other. And so the net magnetization is 0. And that is the characteristic of a thermal paramagnet. Now, if I apply a transverse field perpendicular to the moments, then I can continuously tune the transition down to all the way to 0 at about 5.5 Kelvin. And I again enter a paramagnetic state, but this quantum paramagnetic state has to be very different from this thermal paramagnetic state. Now, because we are at t equals to 0, there is no longer thermal energy for the up and down spins to mix. And therefore, the paramagnet here has to be a superposition of both the up and down states, giving a net 0 expectation value. So the thermally disordered paramagnet and the quantum paramagnet beyond this quantum critical point are qualitatively different. The dynamics of classical and quantum phase transitions is also very, very different. So we know that as we approach the phase transition, the correlation time diverges as well as the correlation length. But when you write down a GL kind of free energy, you always ignore the energy contributions from temporal fluctuations. Why? Because the energy contribution from the temporal fluctuations, because tau is diverging, is always smaller than kBTC, which is a finite number. And therefore, this can be neglected for classical phase transitions. However, this inequality is never going to hold for a quantum phase transition because the TC is 0. And therefore, we cannot ignore temporal fluctuations anymore when the transition is happening at t equals to 0. So to understand such kind of phase transitions, John Hertz in 1976 had given the idea of extending the dimensionality of the system. So giving an effective dimension where D is the spatial dimension and Z is a dimension which depends on the time evolution. So for example, here I have a configuration of spins in space. They are correlated over some length scale, but they are also now changing in time. So in addition to the space dimension, we also have to include a dimension which gives the temporal fluctuation of these spins. Okay. So we have to add some dynamical exponent to the effective dimension. So this is very different from classical phase transitions where you can ignore the temporal fluctuations. But you know, all this physics is happening at t equals to 0, and so why should we bother? Because we can never access t equals to 0. So in 76, it was not clear whether we should be worried about quantum phase transitions at all until 20 years later, Andy Millis came and said that, no, you see, quantum phase transitions or quantum critical points can influence the physical properties up to hundreds of kelvins. So let me see if I have everything here. Right. So let me remind you that here we had a region in which there was order parameter fluctuations, and this region goes smaller as we approach t equals to 0, because the extent of this region is decided by this inequality. So as T goes down, this inequality, the extent has to go down because TC is going down. In quantum phase transition, suppose I'm sitting here where my pointer is. I'm in the disordered region. There is no order here. However, there is also no temperature scale which will decide how strong or weak my fluctuation should be. And therefore, Andy Millis suggested that if we write the only relevant scale is the temperature itself, and if we write the uncertainty principle like this, then we see that the temporal time scale of quantum fluctuations depends on the temperature itself, and therefore the quantum critical point can influence properties well above T equals to 0 itself. So there are other details I don't want to go into because I don't understand them properly, but that is the difference between quantum phase transitions and classical phase transitions. And even though a QCP is sitting at T equals to 0, it can influence properties over a wide range in phase space. So these kinds of phase diagrams, which I showed schematically, seem to be ubiquitous in strongly correlated materials. So this is a phase diagram of a particular cuprate. And you can see that when the magnetic order is suppressed by doping, you find all kinds of interesting phases. The possibility of a quantum critical point hiding here is still being debated, but the point is that up to hundreds of kelvins, there is strange behavior in the metallic state above TC. And similar stuff is found for heavy fermions, for organic conductors, for the iron arsenides, and the Kondo lattice compounds like ytterbium, rhodium 2, silicon 2. And because I'm going to talk about heavy fermion compounds, let me discuss qualitatively how quantum critical points can arise in heavy fermion materials. So they can arise by a competition between two effects called the RKKY and the Kondo effect. So we are looking at the rare earth series, and you can see that ytterbium, which is the element of my choice here, has one hole in the 4f electron, a 4f shell, sorry, and the 3 plus and sorry, can you still see my slides? Hello?
Yes, yes.
Okay. So I had some local problem here. So in ytterbium, for example, what happens is that at high temperatures, we have these localized ytterbium movements in a sea of conduction electrons. So the localized movements are the ones with the red sphere, and the blue arrows are the conduction electrons going around. So at high temperatures, we have these uncoupled two entities. But as we lower the temperature, what happens is that because of CF hybridization, conduction electron and Kondo local impurity hybridization, we end up with singlets. So the local moment are surrounded by a cloud of conduction electrons, which are oppositely polarized. What also happens is that because there are local moments in a conduction sea, they will interact indirectly via the RKKY interaction. So the RKKY wants to order the moments, and the Kondo effect wants to quench the moments. And therefore, there is a competition between these two effects. So qualitatively, if you draw a temperature versus this J interaction between the conduction electron and F electron moments, then you see that the Kondo temperature rises exponentially, whereas the RKKY interaction rises as a squared of the J. And therefore, for small J, the magnetic order wins. But as you increase J, the Kondo effect quenches the moments, and therefore you lose magnetic order and reach a quantum critical point. So this is the qualitative understanding of how quantum critical points can arise in heavy fermion materials or Kondo lattice materials. But even this picture is very simplistic because there are experimental examples of different kinds of quantum criticalities even in the heavy fermion materials. So when there is a phase diagram like this, where the blue regions are the Fermi liquid regions, and the orange regions are the non-Fermi liquid regions, and the quantum critical point here separates these two regions. Then you see that these two seem to be ending at the same point. So even in a phase diagram like this, there is discussion on whether the SDW like scenario holds or the Kondo breakdown scenario holds, where there will be a discontinuity in the size of the Fermi surface as we cross the quantum critical point. But recently, as recent as 2019, people have shown that if you also have these local moments sitting on a frustrated lattice, then you can have a phase diagram which is where these two Fermi liquid phases are separated by a phase which has been called either spin liquid or quantum critical phase, depending on what the material is. And the qualitative understanding is given here. So if you had an unfrustrated lattice, then on this side, where the Kondo screening is not strong, you will get long range order. But as the long range order is suppressed, you enter a Fermi liquid, heavy Fermi liquid, where the Kondo singlets govern the physics. On this side, if you had a frustrated lattice, what would happen as you are coming in from the heavy Fermi liquid is that because of the frustration, the magnetic order cannot condense, and therefore you have this phase is pushed down in phase space. So the ordered phase happens only when the frustration is lifted by a quenching of the formation of one of the singlets, for example. So there are very interesting open questions even in the quantum phase transitions in heavy fermion materials. So that is the reason we wanted to study this. The other motivation for us was that we wanted to look for heavy fermion superconductivity in this material. There are many cerium and uranium based heavy fermion compounds, more than 20, but until recently, there were no ytterbium based compounds, even though ytterbium is a whole analog of cerium. Recently in 2009 and 16, there are two superconductors now with ytterbium compounds, but whether they are heavy fermion or not is still being investigated. So I had started my PhD on this material, trying to address this question. So here I have plotted the ordering temperature versus rare earth, and you see that they scale with the size of the effective moment. What is interesting is that there is also a superconducting transition for many of these materials, not just the non-magnetic materials, but the magnetic rare earths also. So ytterbium from its lattice volume sits in the middle of this. So if I put this here, the ytterbium superconductivity is expected to be at around 4 Kelvin, and this would be a huge temperature for a heavy fermion superconductor. And that is our starting point for looking at this material. Okay, so the crystal structure is tetragonal. There is only one ytterbium site and two iron sites, but both of them are non-magnetic, as has been confirmed by Moss-Bar. So I start displaying the basic physical properties. Here is the susceptibility versus temperature, and you can see that the susceptibility with the field along the C-axis and the susceptibility with the field along the AB axis is highly anisotropic. This can also be seen in the magnetization at low temperatures, where you can see that the C-axis seems to be very hard, much harder to magnetize. So C-axis is the hard axis. The high temperature shows a Curie Weiss, and you recover the full moment here, and a Weiss temperature of -60 Kelvin. There is an anomaly in the susceptibility, which suggests antiferromagnetic ordering at 1.7 Kelvin. Here is the resistivity versus temperature with current along the C-axis, and you see that the behavior is typical of a Kondo lattice compound, where there is a minima at low temperatures and a logarithmic upturn, below which you get a coherence peak and then a downturn. If I blow up this plot, I see that there is at the temperature I saw the susceptibility maxima, you also see a loss of spin disorder scattering. So this is also an indication of magnetic ordering at 1.7 Kelvin. So to get an estimate of the condo temperature, the standard procedure is that you look at the magnetoresistance, because the magnetic field will try to suppress the condo effect. So the upturn is suppressed when you apply a magnetic field. So MR versus field is plotted here at various temperatures. And if this behavior is governed by a single temperature scale, then all of these data can be collapsed onto a single one if you plot it as magnetoresistance versus B divided by T plus T star with the appropriate T star. So we see that there is a beautiful collapse when T star is 5 Kelvin. So the condo effect seems, the condo temperature seems to be 5 Kelvin. The specific heat versus temperature is shown here. The black curve is the full data. The red curve is the lattice, which is the lutetium compound. And then the magnetic part is seen here in blue. The first thing to note is that there is a very large lambda-like peak, which confirms the magnetic ordering. The magnetic peak seems to be riding on a huge background magnetic heat capacity, which is most likely coming from the many-body enhancement due to the condo effect. We will quantify this in a moment. So the entropy is R log 2 only up to about 20 Kelvin. So we seem to have an effective spin half, which is separated from the higher crystal field level. So we can worry about only spin half entropy. The entropy at the ordering actually is only 30% of R log 2, which means that most of the local moment is quenched already at higher temperature, and a very reduced moment ordering is happening at Tn. These data can again be used to estimate the condo temperature, and we get from the heat capacity, we get a condo temperature of about 4.5, which is similar to what we got from transport. These are anyway crossover scales, and therefore you won't get a sharp transition temperature like thing here. So 5 and 4.5 are the same for us. To see if the material is correlated, one does what is called a Wilson ratio, which is just the ratio of the density of states seen in the susceptibility divided by the density of states seen in the heat capacity. And for normal metals, this is of order 1. And for ytterbium, 2 iron silicon, we find 4. So this is a correlated material, clearly. So what happens? This is, of course, at just above the ordering temperature. It's a very heavy Fermi liquid. You can see that the gamma is about a joule, which is huge. What happens at low temperatures? Because beyond the ordering, do the heavy fermions survive? So we show here the C by T versus T square, and the low temperature indeed extrapolate to again a large value of about 400 millijoules. And again, the resistivity at low temperatures can be fitted by a T squared, where the A coefficient again is quite large. So for heavy fermions, one does takes a Kardowaki-Woods ratio, which is just a ratio of the A coefficient divided by the squared of the Sommerfeld coefficient. And this is a universal number for most heavy fermions. So let us see where ytterbium falls on this chart. Here is ytterbium, and these are all the other heavy fermions which are known previously. And we see that ytterbium falls reasonably close to this Kardowaki-Woods universal ratio, confirming that this is a heavy fermion compound. So where is ytterbium placed on the Doniak diagram? Is it closer to the quantum critical point or away from it? So this can be addressed by high pressure measurements, which I show here. So without going into details, let me just say that the ordering temperature is suppressed when pressure is applied. And this is shown here, the Tn versus pressure, and it goes down. So if the ytterbium were located on this side of the diagram, pressure would push it to the left, and therefore the Tn would go up. However, our Tn seems to be going down, and therefore we can conclude that this our material sits on this side of the Doniak maxima. By the way, this is the first ytterbium heavy fermion compounds with a negative Tn by dp. So out of all the hundreds of ytterbium compounds known, this is the only compound which shows this to our knowledge. So this is special already. Now I show you that a magnetic field can be applied to tune the Tn continuously to 0. So this is the specific heat versus temperature at various fields. The fields applied perpendicular to the c-axis, so in the AB plane. And you see that the ordering which is seen at 0 field is suppressed continuously to low temperatures. Additionally, this susceptibility versus temperature at various fields was also measured. And this also shows that the ordering temperature suppresses continuously to 0 temperatures. And we can do various other measurements which confirm this. I would like to point out here that the resistivity versus field as well as M versus field, when you take the derivative, they also show this another anomaly here, weak anomaly here, which moves up with the temperature. So we can start building a phase diagram using these data, and that I have done here. So I show here that the transition temperature, the antiferromagnetic transition temperature, can be continuously tuned and pushed to 0 temperature at a critical field close to 2.8 Tesla. Okay. And this other bumps that I was showing you in various measurements can be plotted here. And this divides the phase diagram into 3 regions, 1, 2, 3. So we would like to find out more about what these regions are. So I call your attention to this graph, C versus T at various fields. So at low temperatures, you can see that as field is increased, the Sommerfeld coefficient is increasing, okay, as one approaches the critical field, which is this brown curve. So if I plot the gamma versus distance from the critical point, so B minus BC magnitude, I will see that when B minus BC is 0, I am at the critical point. So the effective mass seems to be diverging as I approach the quantum critical point. So something anomalous is happening, as has been seen for many other quantum critical magnets. What about the phase 2? So we have established that we have a heavy Fermi liquid in this region 1, and the effective mass diverges as we are approaching this critical point. In the second region, I have resistivity versus temperature at various fields, and this is 0 field, and these are various fields above the critical field. So we are in this region in the middle of the phase diagram. So we find that resistivity is a power law, and the coefficient and the power of the behavior can be plotted here. And at 0 field, you see that the power law, the exponent is 2, so it's a Fermi liquid. But as soon as I enter the critical region, it is 1.3, which is clearly non-Fermi liquid. Also, the coefficient of the resistivity is it's not diverging like the effective mass is, but it's increasing as the critical field is approached. So we have established then that the region 2 is a non-Fermi liquid region. We still don't have measurements on the region 3, so I have put a question mark here, but I already call this a novel quantum critical point because of the separation between the suppression of this ordered state and this what might be the recovery of the Fermi liquid. There is a large region in field and temperature space where there is a non-Fermi liquid effect, but we do not know what this phase is. Is it a spin liquid or something else? And when we try to look at the structure more carefully to see if there were any frustrated motifs lying in the lattice, then we discovered something very interesting. Actually, my colleague, Dr. Sanjeev Kumar pointed this out, that the ytterbiums and the iron form a sublattice, which is the square octagonal lattice. Both, this is the ytterbium, it's a distorted octagonal lattice, square octagonal lattice, and the iron is almost a perfect square octagonal lattice. So what is interesting about this lattice is that recently there have been at least 2 papers that I could find where people have argued that electrons hopping around on such a lattice or even magnetic ions sitting on such a lattice will have topological character. So we are beginning to look at this in collaboration with Tanmoy Das of IISc. But this part of the work is still in its preliminary stage. Yeah, I wanted to mention also that the second iron sublattice actually forms isolated one-dimensional chains running along the C-axis. So one should also be able to see whether these...
You have 5 more minutes, including discussion.
Oh, including discussion. Okay, I'm almost done. So these right. So these 1D chains of irons, which are very isolated from each other, might themselves show charge density wave-like features, which we are exploring. Okay, so this is my summary right on cue. The ytterbium compound that we have studied is a heavy fermion material with a very large Sommerfeld coefficient. It is also a Kondo lattice with a Kondo temperature of about 5 Kelvin. And it undergoes antiferromagnetic ordering of Kondo reduced moments at 1.7 Kelvin. Field can be used to suppress this ordering all the way down to 0 temperature, and this reveals a very interesting phase diagram which is pointing to a novel quantum critical point. We have to explore what kind of I mean, a lot of things have to be done. I can address it if there are questions. There are other novel features about this material. This is the first ytterbium material with a dTn by dP, which is negative. And also, this is the first realization in a real material of the novel square octagonal lattice, which theorists have been pursuing recently in search for topological features in the transport and band structure. So I thank you for your attention.
Thank you. Thank you, Professor Suresh. Nice talk. Now we can take questions, and you see in the chat there are a couple of questions. I also have 1 or 2. So first we can take from the audience. Do I need to read out questions for you?
I can't seem to see the chat.
Can I ask my question?
Yeah.
Yes, Pratap, please go ahead.
Yeah. See, you have a very interesting phase diagram, but then you showed the exponent value n of resistance.
Right.
You showed in 0 field, and then you show in the NFL. How does it evolve in between?
Right. So that is a hole in the data which we have to fill up. We are pursuing that right now.
Because that is, I think, critical to understanding on whether this whole interpretation is meaningful. In the sense that does it evolve continuously and go to that value, or does it have a sort of reasonably abrupt jump at the boundary?
Right. I agree. So this is something we are exploring.
Okay. All right.
Okay. Is there any other question?
Can I ask you a question?
There are many questions in the chat box. You can just...
One question. See, I see this specific heat peak appears above 2.5 Tesla magnetic field.
I'm sorry, I can't hear you. Is this Professor Yusuf?
Yusuf, I think your voice is coming very, very low. Can you go closer to the microphone, or there is something wrong?
Oh, I see. I don't know what is wrong. Is it
Yeah,
okay
now
better?
it is better. Now it is better. You have to go slightly forward. Yeah.
Okay, follow that. See, this specific heat peak, I see it is almost disappearing at 2.5 Tesla magnetic field.
Right.
And then you are, and of course, at lower field, from 0 to up to 2.5 Tesla, the peak is shifting towards lower temperature.
Yes.
But at 2.5 Tesla and above, the peak is disappearing, and you are correlating that as if peak has moved to T equal to 0, and drawn the phase diagram accordingly, and you say that the Tn has moved to 0. So how good is this? Judgment?
No. Not just from the specific heat. So
because if you see a specific heat, that clearly tells that peak is not there at 2.5 Tesla or 3 Tesla. So is it very nice to say that your Tn has moved to T equal to 0 with magnetic field above 2.5 Tesla?
Yeah, please have a look at the phase diagram, where you will see that we have we have tracked the TN using many measurements, including magnetic measurements, which show that the ordering still persists. For example, look at this magnetization versus field, the derivative of the magnetization at 80 milli-K, which is the blue curve. You can see a very sharp peak here. So we have used all kinds of measurements to track the TN, all the way down to 80 millikelvin.
Okay, one more quick question.
Yes, sir.
30% TN and 30% entropy is released left at TN. So that means 70% entropy is already released above just TN. And
Yes.
It is happening over the broad temperature range. So what is the microscopic spin-spin correlation over that temperature range?
Spin correlation, you mean the length or something, or why is this happening?
Above TN, what is the spin correlation?
Yeah,
It's gradually losing the entropy.
Right. My understanding is that the Kondo effect starts to screen the local moments, and therefore the entropy of the local moments will go into the conduction C. And if you look at, for example, ytterbium rhodium 2 silicon 2, where the local moments are almost completely suppressed, you can see a huge Fermi surface, much larger than what would have been there from only conduction electrons. So by hybridization, the local moment is going into the conduction C. That is the point.
Okay. Any other questions from audience?
I have a question. Can I ask?
Yeah, please.
So, Yogesh,
please identify yourself.
I'm Pratyay Ghosh.
Yeah, please.
Yeah. So what I'm asking is, your spins seem to be confined to the basal plane, right? And
from the anisotropy, it seems to be that way.
Yes. Yeah. Is it coming from the crystal field effect or something
Yes.
else?
Most likely from the crystal field, because you see that the single anisotropy is already seen at 300 Kelvin. So it can't be some energy scale which is small.
Okay. And one more small question.
I mean, because of the time limitation. So let us thank Professor Singh for the nice presentation, and we'll move on to the next talk.
Okay. Thank you very much.
Yusuf, just one thing.
Yeah.
You are hardly audible. So just now, Arindam also confirmed that your voice is not coming well. There is something wrong.
Because this is for the first time I have been attending meetings, but I never got this. I have to speak very close? I don't know why it is like this. Is it better now?
Not really. It's coming, but it's coming broken and very.
Because I don't know something.
Okay. All right.
So let us move to the next talk that will be delivered by Shobhik Sasmal from TFR.
Yes, sir. Sir, can I audible? Am I audible?
Yeah, I'm hearing. I'm getting you. So
okay.
The title of his talk is Magnetotransport Properties of Non-Centrosymmetric Calcium Silver Bismuth Single Crystal.
Yeah. Yeah. So this is a great opportunity to talk about crystal growth of calcium Ag bismuth and the magnetotransport properties. So first I start to this is ABC type hexagonal crystal structure, and this kind of hexagonal crystal structure shows different interesting properties, including in LUPD-Bi, the superconducting transition at a low temperature near to 1.8, and weak anti-localization properties, as well as YB-CDGE, the weak anti-localizations, and the HOPD-Bi, as well as superconducting transition and weak anti-localization property. So following that, we prepared this non-centrosymmetric crystals, a calcium silver bismuth. It crystallized in hexagonal structure with space group 186, and the band structure shows that very near to Fermi level it has 3 Dirac points, and at the Brillouin zone at the center it has large hole pocket, and at the boundary of the Brillouin zone it has 3 electron pocket. Small electron pocket. To grow the single crystal, we followed flux growth techniques where we took calcium, silver, bismuth in 1:2:20 ratio, and we took in a aluminum crucible, and we seal the ampule in a we seal in a quartz ampule, and we heated up to 1050 at the rate of 30 degrees Celsius per hour, and we stay there for 24 hours. Then we slowly cool down to 420 degrees Celsius at the rate of 2 degrees Celsius. At 420 degrees Celsius, we have centrifuged it, and we got a nice crystal at the size of almost 1 centimeter. And this is the real image. And for basic characterization, we did powder XRD. The powder XRD shows that phase we are only having very small tiny bismuth peak, because here we used Ag bismuth as a flux, and the Laue diffraction shows clear hexagonal symmetry in the crystal structure, which confirms that the grown sample is single crystal. We have measured the resistivity. So for two direction, I parallel to 1, 0, 1, and 1 bar 1 to 1, 0. For it shows that temperature dependent resistivity is metallic type of behavior. And the Hall resistivity is almost linear, but at 300 Kelvin, it has some very little jump. Due to presence of both electron and hole contribution, this jump can be observed. So this can be explained by two-band model, where we introduce both electron contribution and hole contribution. At 300 Kelvin, we calculated the hole density and the electron density as well as mobility. So when we measure the magnetoconductance, there we have seen a cast-like behavior at low field, and at high field it become almost linear. This surprising behavior always observed in Bi2SH3 crystal also, where it has the sharp cusp-like behavior at a low magnetic field and then become linear. Basically, it happens when the phase coherence length is larger than the mean free path. So when the phase coherence in the ballast in the small diffuser region, so always the charge particle gets scattered due to scattering center. But when the phase coherence length is greater than the mean free path, there, even though after a few number of scattering, the phase coherence always preserve. So in that limit, means the phase coherence length is the larger than the mean free path, there the interference happened between two channel. So I come to that point. So for 2D system, it is so one charge carrier path is coming and in this direction, and other charge carrier path is coming in this direction, and they get interfered due to this large phase coherence length. And while they scattered, this kind of weak anti-localization property can be seen. And this can be explained by Hikami-Larkin-Nakayama model, where the first term comes from the interference term, and the second is due to cyclone orbit term. For 3D bulk limit, we can think for our system is 3D system, but still we can see this weak anti-localization. So for this case, what we can explain that this system can be considered as a large number of 2D parallel conduction channel, where the phase coherence happen for each parallel conduction channel and gives us this weak anti-localization property. So for each conduction channel, if it is one conduction channel, then this alpha value in Hikami-Nakayama model, the alpha value should be half. But for bulk system, as there are large number of conduction channel, this alpha value should be very high. So as I told you, this weak magnetoconductance data we can fit with HLN model, and from there we can calculate the L5, the phase coherence length, as well as alpha value. So the observed L5 value is almost 230 nanometer, and the alpha value is quite large, which conclude that our system has large number of conduction channels. For each temperature, we calculated the magnetoconductance from the magnetoresistance, and and therefore we can calculate alpha value as well as phase coherence length for different temperature. So here is the phase coherence length as a function of temperature. You can see that the as the temperature increases due to the phononic contribution, the phase coherence length reduced. Both the direction, it shows the reduction of this phase coherence length. And if I see the alpha value is quite large for two different directions. To look at the origin of this magnetoconductance, this weak anti-localization property, we measured magnetoconductance at different angle, tilted angle. So theta here is defined the angle between current and magnetic field, and different angle, it shows that the magnetoconductance almost merges at low field, but it's deviate at high field. That means it has more like 2D conduction channel effect rather than the bulk contribution. And so at low angle it's deviates. The normal component of the magnetic field is merging at low magnetic field, also observed other topological semi-metal like Bi2AC3 and others also. So at the summary, I want to conclude that this DFT shows that presence of Dirac points near the Fermi level, and it has cusp-like negative magnetoconductance, which suggests that weak anti-localization properties. And interestingly, it has quite large phase coherence lengths, and the magnetoconductance data is indicating that weak anti-localization is 2D in nature, even this bulk system, and Hall resistivity shows it has quite low carrier density. This work has been published in this Journal of Physics Condensed Matter, and this is our group. And I would like to thank my professor and all the senior professor collaborator who helped me a lot for this work. And this me. Thank you for listening.
Asmal, for
Yes, sir.
completing your presentation. It was a nice presentation, well within the time. Now we can take questions from the audience. Yes. Am I audible now?
Yeah.
Yeah, now your voice is perfect.
Okay, please, you may ask questions if you have any.
Okay, Yusuf, can I ask a question? This is Arindam.
Yeah, sure.
Okay, so Shovik, very interesting material and very nice talk. So I have a question regarding the magnetotransport data.
Yeah.
Are you saying that your Hikami-Larkin fit actually extends all the way up to 4 Tesla?
Yes, no, it can fit even a little larger also, but you can fit with this Hikami-Larkin model that time also. There you will find small beta value, because this value we use this part we have used to fit even larger field also. So for this case, we fitted from -14 to +14 Tesla. Their case, we got very low beta value, almost compared to like 3-4% compared to this.
So I was going to come to that. So the beta value is essentially what you have this Lorentz number, right? I mean, essentially because of the classical component in the conductance dependence on magnetic field. But do you get a number, the beta number, to be reasonable? Because the reason I'm asking, let me just tell you why I'm asking this question. See, I mean, normally whether these surface states are getting destroyed by the magnetic field or not is the question. So normally what in a standard topological insulator, you will, once you break the time reversal symmetry by a large magnetic field, eventually you will break the time, in the 2D surface states, and it will primarily be a 3-dimensional system rather than a 2-dimensional system. Question is whether the beta value is reasonable enough that you say that it is only coming because of the classical component in the magnetic field, and not because there is somehow a crossover from 2D physics to a 3D physics.
No, no. I would rather say this is coming from only 2D diffusion of the charge carrier in the system, because we tried for a larger field also. So 0 to even 14 Tesla also at low temperature. There we have seen also, even not using this beta B square term also, it is fitting quite good. So
okay.
So
okay. It is quite interesting, because normally, I mean, this is at least the kind of bismuth selenide and other kind of standard topological insulators that I have seen. There, the fitting, Hikami-Larkin fitting is usually within
very low field. Yeah.
Very small magnetic fields. Here you are going to 14 Tesla, which is by which there should be no surface states. I mean, where is, so I don't know whether others in the audience can comment on that.
Actually, I can tell one thing. We have also different 3D, I mean hexagonal system ABC type, where we have also seen that even up to 8 Tesla also we could fit with only HLN model, not using plus beta B square. So that is fitting very well. Means the 2D diffusion is so strong that this, even someone can ignore also this beta B square term also.
Okay. So is there any other question? Okay. If not, then let us thank the speaker for a nice presentation.
Thank you.
And we move on to the next talk that will be presented by Sagarika Naik from NISER Bhubaneswar. And the talk is also for 15 minutes. The title of the talk is Role of Spin Glass-like Frustration on Exchange Bias Effect in Bilayers. Those bilayers are iron, iridium 20, manganese 80, and nickel 50, manganese 50, along with cobalt 40, iron 40, and boron 20. So with this, may I request Dr. Naik to make the presentation. Yes, Sagarika Naik. Am I audible? Hello.
Yes, you are.
Yes, you are audible.
Where is the speaker? The Sagarika Naik is present? Yeah.
We can't hear the speaker.
Yeah. I'm requesting speaker to deliver the talk. Dr. Sagarika Naik from NISER Bhubaneswar.
There is some problem. Sagarika, we cannot hear you.
Sorry?
We cannot hear Sagarika. Sagarika,
Okay.
are you saying something? No, I think.
Yeah, I can't hear Sagarika. Yeah. Hello.
There's something wrong. Sagarika, we cannot hear you.
Do you have her mobile number? So then one can make a phone call.
Professor Yusuf, the
Yeah.
speaker has not come.
No. That who uploaded the talk? Because that is from you or from that side, from the speaker side.
The speaker should be uploaded.
Then that means speaker is present. Only we are not able to hear her.
It seems she's speaking also, but she's not audible.
No, I think she logged out. She's possibly logged out and is logging in again.
Yeah, possible. So let us wait for.
She is visible in the list of participants.
Yeah, that is strange. See,
She is speaking.
One should call her. There's something.
We can wait. This is just we have passed only 1 minute. So 13:24 schedule time, now 13:20.
So now Sagarika is visible.
Yes.
She audible. Sagarika, we cannot hear you yet.
Savik, please turn on your
She'll be
mic.
logging out and then again log in. I called her up.
Your mic not.
I think we
His
can
mic
give her
is
some time.
off actually.
Hello.
Her mic is not off. Her mic is on.
Savik, right?
Sagarika.
Sagarika.
Oh.
Sagarika from Naisar. Sagarika Naik from Naisar.
Sagarika Naik. She was visible just now, but her mic is not working.
Now she is not visible. Maybe she is trying to reconnect.
She is logged out. I called her up. So she said that like she had unmuted herself, but we cannot hear him. So she said that she'll be just logging out and again then she'll be logging in.
Okay.
Okay, good.
Let her try. Yeah.
She is now back. Let's see if
I'm audible now?
Yes.
Yeah,
Yes.
very much.
Okay.
Now please share your presentation and start the presentation.
Okay, sir.
Yes, please go to the full screen mode.
Now I'm in full screen mode.
It is fine. It is fine now.
Okay. Yeah, please.
Many thanks for giving me opportunity to talk in the conference. So my talk title is role of spin glass like frustration on exchange bias effect in iron iridium manganese, where iridium manganese is the antiferromagnet, and also nickel manganese cobalt iron boron bilayers, and nickel manganese also antiferromagnets with two different types of ferromagnets. So my motivation, first I will tell about the motivation, my research work. So first, my motivation is to know the interface, qualitative nature of the interface. So first, this ideal model of exchange bias was given, given that the interface is fully compensated, uncompensated. So for that, so in this figure, we can see that ferromagnet is a Welly order and antiferromagnet is a Welly order, but the interface is are exchange coupled with completely parallel, means J greater than 0. So it is actually fully uncompensated. Now when you do this magnetization reversal, because of this exchange coupling at the interface, these ferromagnetic moments takes a very high magnetic field to reverse to the negative direction. Because of this overcome this interfacial exchange coupling, and we get a higher magnetic field here. But when this magnetic field is reversed to the positive saturation, because of this interface exchange coupling supports for this alignment along this positive direction, it requires a less magnetic field to reverse. Therefore we get a shifted loop, and this is called exchange bias. And but the thing is that in this model, that magnitude of exchange bias field that is reported is very high than that value of these experimental results. Therefore next, I'm motivated by this spin glass model. And in this spin glass model, the interface of these ferromagnetic and antiferromagnetic systems contains both rotatable spins and frozen spins, where rotatable spins are low anisotropy and which can reverse during the magnetization reversal of these ferromagnetic spins. However, the frozen spins pins these ferromagnetic spins and try to keep them along a particular direction. And the reason for that and the reason for this glass is that at the interface is interface roughness, disorder, chemical intermixing, structural defects like this. And this is the energy expression that spin glass model, in the spin glass model is used. So in this model they use this effective interfacial exchange coupling because of this presence of spin glass like frustration at the interface, with a anisotropy of the spin glass, effective spin glass anisotropy. And we found that this the two pictures we can see, right side picture we see that interface is completely disordered. When the interface interface is completely disordered, we get a symmetric loop. However, when the interface is little bit disordered, containing both rotatable spin and frozen spins, we it is this model says that there is a shift in this loop and you get action bias. Now this is the different scenario of the interface of a action bias system. This interface of a action bias, this is the collinear interface configuration, and we can see in this this interface is fully uncompensated, where it is in B it is fully compensated, and also the interface can be transverse direction with the direction of these ferromagnetic moments. So now I'll move to my result and discussion section. I will basically describe this study of the interface of this ferromagnetic and antiferromagnetic system, also the role of bulk of the antiferromagnet on these magnetic measurements. So we first decided to study this iridium manganese system, because iridium manganese systems are basically possess very high blocking temperature, and but there are many reports that suggest that the iron grows epitaxially on MgO substrate. So now we are more, but we plan to know, will not do any deposition on MgO, but we'll do on silicon substrate. But there is a large lattice mismatch between silicon and iridium manganese, where iridium manganese is the antiferromagnet. So we decided to deposit tantalum and copper as seed layers to remove the lattice mismatch. And also in this study, we varied the thickness of iridium manganese from 3 to 10 nanometer to study the role of bulk of the antiferromagnet on action bias properties, whereas the ferromagnet iron layer thickness is kept fixed. Now I will move towards my the result section. To study the interface, we perform various magnetic measurements. One of them is this temperature dependent study. To perform the temperature dependent study, we first field cool the sample from 400 Kelvin to the measuring temperature in presence of 1 Tesla magnetic field, and we took the hysteresis loop and calculate the value of action bias field and coercive field and plotted against temperature. In this loop, we can see this is the action bias field versus temperature plot, and this is the coercive field versus temperature plot. We can see there is both simultaneous action bias field and coercive field. There is a sharp rise in this value below 100 Kelvin, indicating that there is a presence of both rotatable spins and frozen spins and at the interface, and they contribute for this large value of coercive field and action bias field simultaneously. So from this spin class model analysis, we can say is the interface is frustrated. Next, we also perform field cooling dependent study to see if this frustration has any role on the action bias field or not. So this is all the same measurement protocol. We field cool the sample from 400 Kelvin to 5 Kelvin, and varied the cooling field from 0.05 Tesla to 5 Tesla, and found that there is a action bias field actually decreasing with cooling field, indicating that the interface is not just like a ferromagnetic and antiferromagnetic interface, because in a ferromagnetic and antiferromagnetic interface, the action bias field should increase with cooling field, because with the increase in cooling field, the pinning moments increases and it increases the action bias field. But because of the presence of frustrated interface, we found the decrease of action bias field with cooling field. Also, we found the decrease in coercive field with cooling field. Next, for study of the spin relaxation mechanism, how the interface spins are relaxed in this the system. So we perform training effect measurements. In the training effect measurement, we first field cool the sample from the 400 Kelvin to 5 Kelvin in presence of 1 Tesla magnetic field, and then we took 10 number of hysteresis loop without doing any field cooling. Only we reverses the magnetic field from positive to negative saturation, and only without field cooling we took 10 number of hysteresis loop, and we found that we can see this is n equal to n loop and this is n equal to 2 loop, and we found that there is a sudden drop in action bias field from n equal to 1 to n equal to 2, whereas there is a no sudden, it is just gradual increase in the decrease in the action bias field with the further increase in the loop number. Therefore, this we could not feed this data action bias field versus n data using thermal relaxation model, which is equation number 1. This is basically suitable for a ferromagnet antiferromagnet interface. However, we found base fields using this equation 2 and 3, where equation 2 is called frozen and rotatable spin relaxation model, and equation 3 is called spin configuration and relaxation model. So next I will describe the data of these two equations 2 and 3 in the next slide. This slide say we found that this you can see this ratio of pi by pf that we calculate from equation 2, where pi is the relaxation rate of the rotatable spin and pf is the relaxation rate of the frozen space, and f is the weight factor, means magnitude weight factor of frozen spins, and a is the weight factor of rotatable spins. We found the magnitude of this weight factor of frozen spins is higher than weight factor of rotatable spins. However, this relaxation rate of rotatable spins is higher than relaxation rate of frozen spins, and we found that relaxation rate interfacial rotatable spins relaxes 8 times faster than frozen spins. Also, we found from this configuration relaxation rate and very low value of order of 10 to the minus value of gamma h. Gamma h basically describes the relaxation here in this model. Next, I'll move to my next talk on this cobalt iron boron nickel manganese exchange bias system. So in this chapter, I will basically describe the nickel manganese, which is the thickness is very increases from 5 to 15 nanometer with a fixed thickness of cobalt iron of 5 nanometer thickness. Again, to reduce lattice mismatch, we deposited tantalum and platinum as seed layer, and then deposited nickel manganese, and we perform to know if there is any phase transition present in the system or not. We perform empty loop in the system and found there is a bifurcation of zero field cool curves at the lower temperature side, and there is a zero field cool maxima in this lower temperature side in this all the samples, and we found that this peak is broadened with the increase in thickness of nickel manganese, indicating that there is the increase in interaction with the increase in thickness of the nickel manganese. So also to like our previous study, in this study also we perform field cooling dependent study to study the interface, to study the role of the interface in these exchange bias properties. So we found similar to the previous study, we found here also there is a decrease in exchange bias field with cooling field, whereas the corrosive field is nearly constant in this study, indicating that yes, there is a presence of spin glass frustration in this system. Also, we performed temperature dependent study, and we found simultaneous decay of exponential decay of exchange bias and corrosive field with temperature, indicating that as the interface contains both the rotatable spins and frozen spins, and which contribute to this maximum value of corrosive field and exchange bias field simultaneously, indicating that as the interface is frustrated. Also, similar to this study, the role of how the interface spin relaxes, the mechanism of relaxation, we perform training effect measurement in this cobalt iron boron nickel manganese system. And for this study, we field cool the sample from 400 Kelvin to 5 Kelvin in presence of 0.05 Tesla of magnetic field, and we have calculate the exchange bias field and plotted with the loop number. Here we have taken 6 number of loops, and we also, like the previous study, we also found that there is a sudden drop in exchange bias field from
you have 3 more minutes including discussion.
Okay, sir. Okay, sir. There is a sudden drop in exchange bias field from n equal to 1 to n equal to 2. Therefore, we could not fit the data using thermal relaxation model, and therefore we have used these two equations, this frozen and rotatable spin relaxation model and this spin configuration relaxation model to fit the data, and the data is well fitted with these two models. Now we have analyzed the data. In this data, we found that this gamma h value that is calculated from this equation 1 is one order of magnitude less than the previous study, indicating that this relaxation, this during field cooling, that metastable state that is created, and during training effect, that relaxation, the relaxation is more in this system. And also we found this ratio of pi by pf, which is the relaxation rate of rotatable and frozen space, that is increases with increase in thickness of the nickel manganese from 5 to 15 nanometer, indicating that that there is not only the role of interface but also the bulk spins of nickel manganese contribute to the relaxation mechanism. Again, to know the if this system, not only the interface, if there is a role of nickel manganese, that it is spin glass or not, we perform AC susceptibility measurement, and we found that is there is a phase transition is present from all the plots, and we found that this temperature TF actually shifted to higher temperature with increase in frequency, indicating that yes, there is a role of spin frustration in the system. So we fitted the frequency versus that peak temperature using Arrhenius law of it to know the system, if the system is super paramagnetic or spin glass, and the value that we have found indicates that not the system is not super paramagnetic. So we again fitted the data using Vogel-Furcher law, and where Vogel-Furcher law is defined here, which includes the temperature TVF, which modified the temperature TF in order to account if there is any interaction present in the system. Next slide, I'll describe with the data, and we found this for a for spin glass system, the tau 0 should be in the range of 10 to the power minus 12 to 10 to the power minus 14 second, which very well agrees that as the system is spin glass like frustrated. So now this is my summary. So we in an iron iridium manganese system, we found this system, the interface is spin glass like. Also we found this presence of spin glass like frustration in cobalt iron boron nickel manganese exchange bias system. So I would like to acknowledge my supervisor, Professor Subhankar Vedanto, for helping me in this work, and also we acknowledge Niger and DAE for financial support. So thanks, many thanks.
Okay, thank you, Sagarika, for your nice presentation. We can take a few questions, but before that, I have one question, that the interface spin glass phase which you talked about, what is this special dimension you need to have this kind of spin glass driven exchange bias effect? Is it a single layer of spin, or is it what is the special extent of the spin glass phase at the interface?
Yes, but we have not know the any PNR measurements or something like that. We have performed to know the magnetic moment, what is the magnetic moment at the interface. But we can say is only maybe if I also said that not only the interface but the bulk spins all contributes also to this exchange bias. But if you not consider any bulk spins, only interface, I can say as one layer of spins or one layer of spin as the model says, but not we have not performed any.
Yeah, because if you have one layer of spin, then to visualize this spin glass, there is a slight difficulty. You can think about it. Now, one more question, that in this quantum conference, quantum phenomena conference, which part of your presentation you would like to correlate to the quantum behavior? Is there any part? You are a student, right? I'm just asking. So, knowing this scope of this conference, can you give some light on this?
No, sir. I have.
Okay. No, this is okay. You can think about it. Okay, from audience, I can take question. Is there any? Is there any question?
Hello.
Yeah,
so
please.
I have one question. So, I mean, can we know the lattice structure at the interface?
You may introduce yourself.
I am Vikas. So I have one question for the interface. I mean, can we know the lattice structure? I mean, that's a hexagonal or honeycomb or some triangular or something like that.
As for our iron iridium manganese system, we perform grazing incident X-ray diffraction study, and we found that both these iron and iridium manganese as cubic structure, not tetravalent. So it is basically texture growth and a cubic structure with 111 lattice constant HKL
The
values.
surface is your magnetic elements are forming some sort of structure. Is it frustrated automatically, or is it
No. This the interface is basically frustrated because of interface roughness, can be disorder and lattice mismatch. This plays a role actually for this interface. We are just we are giving just qualitative study on this to know if the interface has any effect on magnetic properties or not. But the role that spin glass interface comes because of this roughness, lattice mismatch, and disorder, all the things because of that only.
Okay, thank you. Is there any other question from audience? Otherwise, we'll close this particular presentation. Okay, let us thank Sagorika Naik for our presentation. And now I understand that organizers have given me the opportunity. If Professor Vikas Chakraborty is still available, we can take his call. Talk. Is Professor Vikas Chakraborty available?
Sir, I'm calling him. He is available.
Yeah, then could you connect him?
Yes, sir.
Yes, Professor Vikas Chakraborty. Hello.
Sir?
Yeah.
Yes. Yeah, I will start from the title page, okay? So then I will.
Yes, only request is Professor Chakraborty. Professor Chakraborty, only request is that if you can finish your talk, 20-23 minutes, that will be nice.
Sir, please hold on. Sir, please hold on.
No, I am only requesting that please try to summarize your talk by 20 minutes or so.
Okay, sir, 20 minutes এর মধ্যে স্যার শেষ করতে হবে স্যার এখানে যিনি চেয়ারপারসন আছেন উনি বললেন 20 মিনিটস এর মধ্যে শেষ করতে হবে
So you can give more highlights rather than going into very detail because
হ্যাঁ উনি হাইলাইটস করে মানে দিতে বলছেন
yeah, exactly.
হ্যাঁ
I will try to finish before that. Yeah. So tell me when to start. Yeah.
Okay, you can start now.
Yeah, please start.
So I will resume this. I was discussing that that in a many body system that can be a long out type of scenario that this is the typical scenario that you have one ground state and it's a kind of double well situation in the energy or free energy landscape. But you can have frustrated random disorder like in spin glass where you cannot transform away the disorder. If you could transform away, of course, if you would go back to the ferromagnet scenario, but otherwise it will be spin glass where you have kind of rugged landscape and the system becomes non-ergodic because you have a large number of barriers which are of the order of the system size, N. So as you can see in the lower left panel, where free energy versus the configuration number for N spins, there are 2 to the N spin, 2 to the N configuration. So in the configuration space, this is like this. Of course, there is a symmetric part as in the upper one, but that I have not drawn. Anyway, since it is non-ergodic, the each portion of the landscape has its own order parameter, and that distribution will be looking like this, and this is in the N going to infinity in the thermodynamic limit. So it is not going to become a delta function as in the Landau case.
Okay, so now I'm showing the second slide, ferromagnetic versus spin glass energy landscape.
Yeah. So this is the thing. Now this we discussed. Now in the I am still in that slide, ferromagnet versus spin glass energy landscape, and you can see that to get the ground state in ferromagnet kind of situation or this kind of many body systems, you just change the local change the configuration. Say in this case the spin configurations locally, and if its energy is lower, you just accept it, and you will hit the ground state. But in the spin glass phase, you can easily see that you will not do that. You will be coming to a local minimum, and then if you have to do, the energy will only increase. Now, if you throw away higher energies, then you will not going to go anywhere. So the idea by Kappa trick was the simulated annealing was that you accept if it is lowering the energy, accept that kind of change. But if the configuration change is giving a higher energy or higher cost, then you accept it with a probability given by like a Boltzmann probability that minus change in cost or changing energy divided by a noise factor, which is artificial or simulated one. You first keep the temperature artificial noise very high to see the entire landscape, and then you decrease the temperature, anneal the system so that it eventually comes to the ground state. That was the classical simulated annealing. The problem was that, I mean, in the thermodynamic limit, if there are these kind of barriers are going to infinity, then any thermal system cannot do that and it gets blocked. So let me come to the next slide, tunneling picture. Then you can see that, I mean, suppose you have a simplistic situation, one barrier of height of the order of, I mean, you can see in the middle I have written order of n, delta V, I mean, that's the barrier height. And before that, I mean, on the left-hand side, there is a kind of potential which is V1, which is much smaller than the barrier height, and then you have outside which is V2, which is slightly less than V1. So essentially, in a thermodynamic system, I mean, you can give sufficient time and temperature, thermal noise will take the system out. What would be the escape time? I mean, the barrier escape time, you can see the thermal jump probability is written there. It is exponentially decreasing with the barrier. Divided by the noise. I mean, the kinetic energy has to occasionally come to the that value, and that will be the probability to get out. So this is the probability, and that says that the barrier is proportional to n. And since the barrier height is proportional to n, the thing is e to the probability is e to the minus n by temperature, and that the probability is this. So escape time is proportional to e to the plus n. So, whereas in a quantum case, you can easily see that there is another parameter which can be of very advantage. The width of the barrier doesn't come in the classical picture. You can see that in a minimal estimate is like this, that I mean, suppose a plane wave coming, and the amplitude A is on the left-hand side is A, into the I case, and that after kind of tunneling through, the barrier is the amplitude A dash, and I want to find A dash, A by A dash, and that square of that will be, or A dash by A square will give me that, I mean, tunneling or escape probability. Again, it will be a plane wave. Now, the thing is, in between, essentially, your momentum vector will now change from E minus E1 and E minus V will now be V minus E, and then you take the I outside because V is, I mean, the delta V is much higher. So, kappa, which is the damping factor here, because the A has now become complex, I mean, imaginary. So, that I kappa, then I kappa is essentially delta V minus the square root of that. Now, delta V is of the order of n, and E, the kinetic energy you can assume very small. So, essentially, it is a square root of n minus V. And then you can see that already quantum tunneling says that the tunneling probability goes as, I mean, the escape probability goes as e to the minus of square root of n if barrier height is proportional to n, then square root of n into width, and then divided by the kinetic energy term. But the thing is, the width, if the width first is already because of this thing, I mean, already e to the n has now become, e to the minus n has now become e to the square root of n. That is an advantage, n is the system side. Also, there is a width. Now, if the width goes to 0, as in a delta function is penetrable. Although, thermally, it would never be possible because you would have to give infinite energy, and then you cannot, I mean, otherwise it would not get out, and that's not possible. So, at any finite temperature. But here, for a delta function barrier, I mean, we know that, I mean, it is penetrable, and So at finite things. So that is the advantage, and so that's the advantage of quantum kind of tunneling, and to make such systems possibly ergodic. Now let us come to the quantum Sherrington-Kirkpatrick model. So this is the next slide, quantum Sherrington-Kirkpatrick thin glass model. So have you come?
Yes, sir. Yes, sir.
Yeah. Okay. So now you have H is H0. H0 is essentially SK model Hamiltonian, and you will see that Jij is of course random. There is a Gaussian distribution. It can be positive and negative. I have made it around 0. So and then you have the Ising spins. Sigma I, sigma Z, and the interaction between them is Jij, and Jij has a Gaussian distribution. But then I put it in a quantum field in the sense that gamma, sigma x, and you can see that sigma x will actually flip the eigenstates of sigma Z. So the flipping probability will be given by gamma. So gamma is usually called the tunneling probability or tunneling field. So this is the transverse field, and you can put it on the longitudinal field, which I have not done in this Hamiltonian. But then this can be at a temperature T, and which will also allow flips. But even if the temperature is not there, the flips will be allowed by the tunneling probability. So if gamma is very high, capital gamma in Hi is very high, then of course the system will become paramagnetic again. And if the temperature is very high, then of course the temperature will take it to a paramagnet, from thin glass to a paramagnet. So there is a temperature and gamma plane, there is a boundary that is actually that has been. So if you want, there are the detailed discussions in this. So let me go to the next slide, Suzuki-Trotter formalism. Now this is just to make the whole thing. I have to skip the details to make this quantum system in an effective with an additional dimension of time, Trotter time. It becomes a classical one. So that's the thing. So let me now go quickly to the Monte Carlo simulations. So we find the single order parameter and then try to find the Binder cumulants. Again, given the references, so the Binder cumulants are, okay, technically these are well known, but anyway, I have to skip this. So we try to find the next slide, scaling of the Binder cumulant. So scaling of the Binder cumulant, are you there?
Yes, sir.
Yeah, okay. So now the Binder cumulant scaling behavior, of course, the system size L and the Trotter dimension is M. So they should, that scaling behavior, if you fit properly, you will get the sum of the exponents like correlation length exponent, upper critical dimension, and the dynamic exponent. In the time dimension, it will give the scaling fit will give us the dynamic exponent also. So we tried to find that, and we found, these are the, okay, now come to the Binder cumulant at high T. Next slide, Binder cumulant at high T.
Monte Carlo simulation.
Yeah, Monte Carlo simulation page is over. Then we are coming to the Binder cumulant high, Binder cumulant.
Yeah, this is okay.
Okay.
Okay. And yeah, so then you can see that the D function and the Binder cumulant is crossing. This is a classical case because I have put tunneling field 0 here in the upper left. The upper right one has some temperature, very small temperature, and gamma is the tunneling field, and it is crossing. Similarly, for different system sizes, it is crossing, and so system. This we try to find at different temperatures and gamma to find the phase diagram. And so this is the next one is Binder cumulant low T. So that. Are you there?
Yes, sir.
Yes,
okay. So Binder cumulant low T is also giving us the crossing point, but you can see that it's very almost touching after the crossing, but it is actually crossing. And through this, then the next curve is collapse, but that is using that helps us to find out the critical exponent. And so these collapses help us to get the collapse, critical exponents. So next one is this collapse are at lower temperatures and higher temperatures. And so next slide, collapse of G curve continue. Okay. So again, we find, from this, we find that higher temperature, we get DC, that upper critical dimension to be 6, get the dynamic exponent to be 4, and X for these things. And then for our simulation for the low temperature quantum case, that is giving DC 8Z2, the dynamic exponent, upper critical dimension 8Z2. And this gives X tau, this DC into nu to be about 0.5. So that is the thing, and we tried also some exact diagonalization studies. Of course, the system size is smaller, so that is exact. So next slide, exact diagonalization line job. So I will just skip that, and so zero temperature result. Similarly, G functions were, the next slide, zero temperature result. Okay, zero temperature result. Okay, so now one can collapse them and get also this X tau, X gamma, that is DC into nu. Again, 0.5 for the quantum case. So that, and also we found the critical tunneling field. So we tried to estimate the zero temperature result, from the zero temperature result, various quantities, essentially gamma C. This is the phase diagram that has been obtained kind of before us earlier, but we not with these details. So this is the phase diagram. What we found is that, you can see that, if it is gamma is 0, this is the phase diagram. Next slide. Next slide, phase diagram. Hello?
Yes, sir, phase diagram.
Next slide, phase diagram. So now one can see that in the temperature and tunneling field, the SK model, the Sherrington-Kirkpatrick model, in a triangular field at a temperature T. Now, without tunneling field, this line, x-axis line, that transition is well studied. And then zero temperature tunneling field was also studied, and here we have given some numerical results to show that this is the thing. Most important is, and of course, we can get from the Binder equivalent collapses, Binder equivalent crossing points, you can find gamma C and PC for different values of C and gamma. But anyway, from singulars to paramagnetic. Now, what we find is that the critical behavior along the boundary, phase boundary, changes dramatically. We say that we can find out the Binder equivalent crossing fluctuation magnitude, GC, 0.22 for the higher temperature case. It kind of drastically changes to something about 0. And then critical exponent from half to, new correlation length exponent shifts from half to 1/4 around the lower temperature crossover point. So this is the interesting thing that we tried to find out. So let's go to the next slide. Ergodic region of the quantum singular. Ergodic region of the quantum SK model, tunneling effect. Are you there?
Yes, sir.
Okay. So now this summarizes the essential findings. Okay, the two publications give that. And these are mostly, but there are other things also. Essentially, this blue region seems to be ergodic-like. Where I do not have much time, and this red region is non-ergodic as in the classical. This is the Parisi region. The red region is Parisi region. Blue region is somewhat Landau region type. Now, to get the tunneling, this annealing time is not, in the ergodic region, is not, this is the upper right corner annealing time changes with S. S is a measure from the quantum expansion line towards the higher temperature. So if you are within, this light arrows are in the blue region says that I have decreased the temperature and gamma along this line. From para to I have tried to come to the singlet. So if we do that, to get the singlet ground state, the time required is not dependent on the system size. This is a signal of an ergodic-like system. Whereas in the red region, you can see that as we increase S, along the phase boundary, starting from the quantum line, T equal to 0 line, as it increases, it starts depending on the this thing. So this says, now this blue region is more ergodic-like. It is Landau-like scenario, and this region is non-ergodic, as in Paris original classical spin gas. So this is the thing. Actually, so annealing in this region, annealing in the blue region will give us much faster annealing and coming to the solution or the optimization problems and so on. So all these things are somewhat discussed in a book by us, and it was in 2017, but there was a Japanese translation last year. It is 2018. And that concludes my my presentation.
Okay.
And thank you.
Thank you so much, Professor Vikas Chakraborty. So to finish within another 17-18 minutes. So now we can take.
It's difficult, but if there is any question, I can try.
Yeah. So if there is any question.
Please write it in a chat box. I will read it to him.
Yeah. If there is any question, please.
I will write it in a chat box. Okay.
I will read it to him.
Okay.
Okay.
Can I ask one question? Is it?
So if you write in the chat box, then I will read it to him.
Oh, I see.
Yeah.
Okay. Yeah, Pole. Okay, sorry.
Hello.
Sir, please wait.
Okay.
Sir,
You get my question?
Sir, it has not come yet. Yeah.
Okay, sorry.
Yes, come. Sir, Mr. Yusuf sir.
Yeah.
Yusuf sir has a question that Hamiltonian does not have the quantum fluctuation terms, but the phase diagram is at T equal to 0 Kelvin.
So,
okay, let me come to the Hamiltonian. That is, let me tell you, it is, let me come to the Hamiltonian, and that is actually fourth slide from the beginning. Okay. So, can you come? Yes, first is the, okay, then ferromagnet versus spin gas, then tunneling picture. Have you come there?
Tunneling picture, then?
Then comes the quantum Sherrington-Kirkpatrick spin gas model.
Yes, sir.
This slide. You have come there?
Yes, sir.
So we show that. And so this is the Hamiltonian. Now,
yeah.
The Hamiltonian has H0, which is, of course, the classical spin gas SK model, Sherrington-Kirkpatrick model. But then it is put in a transverse field, non-commuting field. The original H0 is the original SK model. These are only jet component of the Pauli spin. Sigma I jet, sigma J jet, Di interaction among them, which is random, plus minus, and that is given by the distribution given by the Gaussian probability below. Rho Jij is the distribution. But then you have some plus Hi. Hi is contains sigma Ix. Sigma Ix doesn't commute with sigma J. So this is a non-commuting field.
Yes.
This sigma Ix actually changes the eigenstates of sigma J, Ij, from plus, that means 1, 0 to 0, 1. So this state actually flips. Up spin becomes up, Z component spin becomes down spin, and the probability of that change will depend on the tunneling field. So it is this quantum term which is actually responsible for all these advantages.
Okay.
We consider, of course, the whole system in a thermal path. So temperature is also there. So now come to, now I have to jump to tell you where is the, so let me now go to next, the phase diagram. This is actually 16th slide. Phase diagram. So now you can see this is on the y-axis the tunneling field that was shown, that is connected, that is the tunneling field is actually this field was the amplitude of the sigma x term in the Hamiltonian. Sigma x doesn't commute with the sigma z in the Sherrington-Kapratzi model. So cooperative interaction is between sigma I z and sigma j z. And their interaction is Jij, which has a Gaussian distribution. So that is the original SK model thing. Then you put it in a transverse field. Transverse field is amplitude is gamma, capital gamma, and it is coupled to sigma x. So it is not commuting. So that will give me the tunneling from one eigenstate of sigma z to another eigenstate of sigma z.
Okay.
The whole thing is put in temperature part. So that temperature can also drive the transition from syngas to para. Lowest temperature will be syngas and it will go to para. So that is actually the x-axis. That is the well-known.
Okay. Only we can take the next question. It is last question.
And of course, the critical behavior that is indicated in the blue along the blue line, nu equal to half, dc is equal to 0.22. The Binder cumulative fluctuation at the critical point is around 0.22. These are well established. So this does not go. So this is in the same phase diagram.
Okay. It is understood. Now, could you kindly take the next question?
To the quantum thing. Quantum thing. Yeah.
We have a next question from Amit Dutta.
Okay. So that's
Yes. Is it a phase transition from the ergodic phase to Parisi phase along the phase boundary? What is G_C?
Not. What is?
G_C.
In this phase.
G_C. Oh, this is the upper critical dimension when this mean field behavior will be fitting. Because this is SK model is actually long-range interacting spin model. So whatever critical behavior comes, this should correspond to the highest, upper critical dimension and above.
Madam, this is not the question. Question is what is
DC? If you start from short-range interacting spin, yes.
This hold on, Yes.
Question is what is GC?
What is DC?
Not DC. G.
GC. GC is the Binder cumulative. Okay. Can I come back again? Let me see.
It is in this phase diagram only. I can see.
Go back. For example, slide number 9, Binder cumulative high temperature, high T. This is 9th slide from the beginning.
Ferromagnetic, then tunneling.
No. Then ferromagnetic go past and then Binder cumulative.
Binder cumulative high T.
High T, yeah. So now you can see that there is a Binder cumulative G are actually crossing at some point. all with different system sizes. For example, red one is for n equal to 60, and black one is for the 540 pin. The 60 pin one is red, 540. I mean, in between there is 180 pin, and that is blue triangle. Now they are all crossing at some point. Now where this Binder cumulant is, Binder cumulant, remember Binder cumulant is actually fourth order fluctuation of the order parameter, average of that, and second order fluctuation, square of that, average of that, and then second square. Now, in a sense, if the fluctuations are have a constant, I mean, there is a constant plus some fluctuation, then of course it will become some one or something. Otherwise, it will go to zero. If it is Gaussian, if the fluctuations are Gaussian, the Binder cumulant is designed in such a way that this value of g, small g, will go to zero. And if there is not much fluctuation, then it will go to 0.67.
Okay, we have to stop the discussion here because it is already 2:15.
So now, just a minute. So this will be crossing at a point where correlation length, because the function, it will be a function, scaled function of the length, system size.
Could you kindly convey to him that we have to stop the discussion?
The correlation length goes to infinity, so it is not dependent on n. Yeah.
Chairperson is saying it's already, time is up.
Yeah, because now we have to stop here. And with this, let us thank the speaker, Professor Vikas Chakraborty. So with this, I thank not only Professor Vikas Chakraborty, but all three other speakers, all four speakers of the session.
Thanking all the speakers in this session.
Okay, thank you. So with this, I close this session. Thank you.
Professor Yusuf, thank you very much for chairing the session.
Okay, thank you. Thank you.
I'm also sorry, at the beginning I was supposed to introduce myself, introduce you by myself, but due to signal strength issues, I couldn't do it. I think there was a little bit of inconvenience with that. I'm very sorry. So
No, sorry. No, I didn't get what you said.
At the beginning, I think I was supposed to introduce you as a chair.
Yeah.
And I couldn't do it because of signal issues here from my home.
Okay. So in fact, I was waiting that I thought, should I start just like that? So I was, I was calling. Okay, but no problem.
Usually one of the organizing members.
Then I was wondering something probably a connectivity problem. But anyway, this is what is our life. Okay, thank you so much for giving me the opportunity.
Thank you very much for chairing this session. And with that, I think we are done with this session. So we'll be starting again at 3 p.m. So let's reconvene at 3 p.m.
Yeah. Okay. Let us close it.